Welcome to the Bible and Science. This is Dave Prentice. I'm a retired public high school teacher, certified in all branches of science and math. I've also taught on the Bible and Science for many years, both in the U.S. and on many overseas mission trips. This is episode 14 of the Bible and Science podcast. It will get into a few little technical things, so just hang on, and if you need to fast forward at those times, do so, but please, you may get something out of this. The questions here are, how is the universe developing in the present, and then in the past, how did it develop? That is it going from simple to complex or complex to simple? And then, how persuasive is the case for a Big Bang? Remember, I've brought this out before. Any model of origins has to deal with at least four major areas. Number one, how did matter and energy come into existence? We talked about that in the last session, and there is no natural explanation for how they could have come into existence from nothing. Well, number two, once matter and energy somehow came into existence, how did they get from the beginning conditions to the present state? That's most of what we're going to talk about tonight. And then how did life begin? And then once life began, how it got from there to its present state. That's going to be some future sessions. Okay, how did matter and energy come into existence? This was the subject of episode 13. In Genesis 1:1, God created the heavens and the earth. The Hebrew used was bara, and it's usually taken to mean creating from nothing. In Genesis chapter 1, verse 26, he said, "Let us make man," Hebrew nase. That would seem to indicate that he used the matter he had created previously rather than creating new matter. So you read about that where he gathered up the dust of the earth and put it together into a human body. Then in Genesis 1:27, it says he created man. So even though he had in the previous verse made man from previously existing matter, this is back to a variant of bara. And in this context, he was creating the essence of humanity from nothing rather than from pre-existing material. So then in Exodus chapter 20, verse 11, God wrote with his own finger that in 6 days he made the heavens and the earth and the sea and all that in them is. In this case, it was the Hebrew word asa, which indicates that he used the material he had created previously. So first he brought matter and energy into existence, and then he worked with what he had done. He rearranged it, with the exception when it came to creating the spirit, the soul of man. He created that from scratch. So how did the universe get to its present state? First, there is no known natural explanation for how matter and energy could have come into existence. Second, the size of the universe, we'll talk about that somewhat in this episode. In later episodes, we're going to talk about the origin of the organization of the universe. Could a Big Bang produce the structure of the universe? And after a while, we'll get around to talking about the age of the universe. And then, is a Big Bang the most likely explanation for where the universe came from? So we would automatically predict, according to the concept of creation and evolution, certain things we should expect to find in nature. Creation says complex to simple. God started everything at its maximum complexity, most organized. So there should be a built-in tendency toward deterioration and disorder throughout nature, a tendency. Not instant, not always, but a tendency. Evolution, on the other hand, goes from simple to complex, supposedly. So since the universe has become more and more organized, there should be a built-in tendency toward increasing organization and order throughout nature. Those are our predictions. Well, what do we actually observe? We observe something called the second law of thermodynamics. thermo indicating heat, and all energy can change to heat. So the second law of thermodynamics says that energy expended in a closed or isolated system, that is, you don't have outside influences, that energy is going to move inexorably toward increasing entropy, disorganization. That is, the universe is deteriorating. This is not theoretical. This is observational. We've been watching this for several hundred years and seen that, oh yeah, the universe really is deteriorating. It's going from complex to simple. That's really tough for evolution to account for. So speaking of the concept of entropy, which is disorganization or randomness, when it comes to energy, energy tends to flow from greater to lesser concentration. That is, it moves toward equilibrium with its surroundings. And as energy is used, more and more of it becomes randomly distributed as useless heat. It doesn't go out of existence, it just gets randomized and it's just spreading out through space. Now, when it comes to physical structure of matter, because matter is held together by stored chemical energy, it too tends to move toward random distribution and equilibrium with its surroundings. Information, this is an interesting concept. As structure breaks down and energy is lost in the form of random heat, the system's information content decreases. Information, that's the instructions that would be necessary to duplicate a system. So the more instructions it takes to reproduce a system, the more information it contains and the lower its entropy. As structure breaks down and energy is lost as random heat, entropy increases and information content decreases. You wouldn't expect something like an automobile, which is just parked outside for 100 years, to get more and more and more organized. We know practically things are going to decay, they're going to deteriorate. Information content has never been seen to increase by itself in either open, closed, or isolated systems. Open, anything, well, a lot of things can get in and out. Closed, well, energy can get in and out. Isolated, nothing can get in and out. Let's think back to that word, thermodynamics. It has to do with the flow of energy. I was challenged once when I was giving a talk to a group of university people to define what is energy. We don't have a good definition of energy. What we can do is say, well, energy is the ability to produce change. And I would always joke with my students and pull a bunch of coins out of my pocket and say, see, I'm like energy. But energy is just the ability to produce change. So can things happen by themselves? That would be a thermodynamically favorable reaction. Exothermic, which is pretty much a synonym for thermodynamically favorable, it would release more heat energy than it takes in. It can occur spontaneously in a closed or isolated system. For example, breaking down complex molecules such as DNA and proteins, burning oxygen, joining hydrogen and oxygen to form water, things like that. That's thermodynamically favorable. You don't have to really do anything. It'll go by itself. You might have to give it a little energy of activation, but generally it'll go pretty much by itself. Now, on the other hand, thermodynamically unfavorable reactions. These require more energy than they release, so we could say they're endothermic. They can occur in open systems, but they've never been seen spontaneously occurring in an isolated system. Energy's got to pay the cost. The universe has to pay for it. So some examples of thermodynamically unfavorable reactions would be formation of DNA and proteins, manufacture of gasoline, separation of water into hydrogen and oxygen, things like that. So when I say the formation of DNA and proteins, when something dies, the proteins are breaking down. This is something that's thermodynamically favorable, breaking them down, but putting together those things in the first place, no, that's unfavorable. That will only happen in the presence of something like DNA that's guiding the whole system. So what will happen to the universe? Entropy is a measure of disorganization, deterioration, randomness, what have you. So entropy tells us, or the second law of thermodynamics tells us, that entropy is continually increasing, steadily, inexorably flowing from greater to lesser concentration. For example, the potential energy in stars, the gravitational potential energy, the nuclear potential energy, it's converted to light, heat, other forms of radiation, and they spread out through space. Given enough time, all the stars will burn out. The universe will wind up being lifeless and cold, just a few degrees above absolute zero. It's a one-way process. I was giving a talk in China some years back, and I talked about thermodynamics. The students were raised as atheists, and I talked to them about thermodynamics, that the universe is deteriorating, it's falling apart. And one of the students raised his hand and said, well, what will happen to the universe? I said, it'll die. He said, what can we do about it? I said, absolutely nothing. There is no way human beings can stop the process of deterioration, of increasing entropy. Now, the only one that could stop that would be the one who made the universe in the first place. I believe God will fix the universe, but if you don't believe in God, if you're an atheist, you have no hope. So let's talk about those systems that are open systems. For instance, the Earth is an open system because we have energy coming in from the sun. A lot of evolutionists will tell us that, oh, entropy can decrease in open systems, things can spontaneously come together. Well, there are certain conditions necessary for entropy to decrease. Number one, there has to be a supply of energy coming from outside that system. So we've got a new developing human being, that's a system, got to be a supply of usable energy coming from outside. Well, okay, a bomb's got a great deal of energy. Let's set off a bomb next to a baby and see if it grows. No, it has to be a usable form of energy, the right kind of energy that the baby could use. It got to be in the form of chemical energy in food. So it's got to be usable. And then there has to be some sort of a conversion mechanism to put the energy into a useful form. So if you pile up steaks and lobsters around a baby, the baby's going to starve to death because the baby's digestive system is not yet able to process the kind of foods that you're giving it. There has to be a conversion mechanism to put the energy into a useful form. And then you can give the baby all the energy you want, but it's not going to come together into a human body unless there's already pre-existing instructions, that is DNA, on how to use that energy properly. So I don't care how much energy is available. If there's no instruction plan, no DNA, there's going to be no growth. Now, this is where some people that are staunch believers in evolution really don't seem to understand. They'll say, well, things get orderly all the time. For instance, two hydrogens can come together and they'll form a water when you put them with oxygen, and then they'll come together and form ice crystals. Okay, crystals form not because of an increase in information, but an increase in order. For instance, water molecules always have a bent shape. We've confirmed this with X-ray crystallography for a long time. They have positive and negative ends. They're more or less a triangular shape, a bent shape. But as long as water is in the liquid or gas form, the molecules move too fast for that negative over by the oxygen to link up with the positive by the two hydrogens. They're moving too fast. But if you slow things down, that is, if you remove heat, where does the heat go? To the universe. So when enough heat is removed, then they'll slow down, link together, and form ice crystals. There's no more information in a molecule after it becomes part of a crystal than before it did. The only reason crystals are able to form is that the entropy of the use is increasing due to the heat released. So there's a chemical equation, delta G equals delta H minus T delta S, if you want to look that up in your chemistry books, where the Gibbs free energy is negative. There has to be energy released to the universe. Otherwise, it won't happen spontaneously. Well, what do you mean? This is all just random stuff. Okay, let's take a random arrangement of letters, as you see on the screen. I just took some letters, and you'll see which letters in a minute, but I just put them together randomly. What do they mean? Absolutely nothing. Well, okay, let's do what the evolutionists want. Let's make them orderly. Oh, yeah, look at that. Look how orderly it is. What does it mean? Absolutely nothing. There has to be not just order, but organization. Here's what happens when I organize those letters in a certain way. They say, "For God so loved the world that he gave his only begotten Son, that whosoever believeth in him should not perish but have everlasting life." It's the same letters, but there's a great deal of information contained in those letters now that wasn't there when I just put them in an orderly fashion. So if you want something to be alive, you don't randomly arrange the atoms and the molecules in alphabetical order. They have to contain information. So if I've got an open system, like a new little human body, and I want entropy to decrease, well, okay, first there has to be something coming in from outside. It's got to be a usable form. For instance, in a baby, it's got to be food energy, chemical energy in the food. Then there has to be some sort of a conversion mechanism to put the energy into a useful form. You need the baby's digestive system. Then there has to be pre-existing information in order to use the energy properly. DNA guides the way that the molecules are put together using the food energy. And then how's this going to happen? As entropy decreases in the open system, it has to increase by a greater amount at the source of the energy. There's always a cost. The universe has to pay for it. So you give a kid a hamburger, and he or she processes the hamburger meat to build together human structures. Yeah, but where did it come from? The hamburger meat came from a cow. How did the cow come together? Because it got chemical energy from the grass. How did the grass come together? It got chemical energy from the sun. It got radiant energy from the sun, converted it into chemical energy. So the sun paid for it. It doesn't happen spontaneously. It's got to have a payment. Entropy has to increase in the open system, bigger open system, by at least that amount. There's always a cost. So you might have heard of chaos theory. This says that, well, sure, things can become organized on their own. Well, there was even a Nobel Prize awarded regarding chaos theory, but it's only a mathematical model. It's never been observed in nature where things are going to come together and form spontaneous pockets of organization. It also deals with chaos only on a microscopic scale, and it's irrelevant to evolution because the local areas of organization in chaos theory are transient. Evolution requires areas of stability that are building on one another for billions and billions of years. So let's think about how things are developing in the present versus the past. Somehow that DNA came together in the first place for humans and cows and grass and so forth. Well, how do we know that? We can speculate, we can come up with models and so forth, but the things we can look at in the present, we can use observation, we can use inductive logic, which is where you examine many phenomena and find the most likely explanation based on your observation. But when it comes to the prehistoric past, there's no living person that has personal experience. And there are no eyewitness accounts except the Bible, which is unacceptable to skeptics. So how would we know about the beginning apart from the Bible? Well, deductive logic. That's where you start with certain postulates, certain things you accept as given. They have to be true, and you develop your system of logic. Well, of course, you can't really be sure about the postulates, the presuppositions of your deductive logic. So let's think about the way things are out in space. How do we know how things got the way they are way out in space? I don't mean by the moon. I mean far, far, far away, many light years away. How do we say we know these things? Mainly by deductive logic. We have certain presuppositions we base this on. So you could start in a number of different ways, but I'm going to start by talking about how big is everything. How do we know what's happening in space? Well, what do you mean space? Humans have never gotten farther away than the moon. We've had several human beings land on the moon and come back. That's about 250,000 miles away from the Earth, approximately. Takes light about 1.25 seconds to travel that distance. So the moon is about 1.25 light seconds away. That would be the distance light would travel in that many seconds. The furthest objects human beings have sent out are several space probes that have left the solar system. Voyager 1, for instance, it's estimated, is about 15.5 billion miles away. It took it 48 years to get that far, but it only takes light about 1.25 hours to travel that distance. So it's moving nowhere near the speed of light. If you're going to talk about cosmic distances to stars, galaxies, and so forth, you normally don't express those in light seconds or light hours, but in light years. A light year is just under 6 trillion miles. That's about 400 times as far away as the Voyager probe, and Voyager took 48 years to get there. The nearest star, Proxima Centauri, it's about 4.25 light years away. So our farthest space probe has only traveled about 6/10,000ths of the distance to the nearest star in 48 years. So how do we know how far away things are in the solar system? Later we'll get back to outer space. But in the solar system, Johannes Kepler, several centuries ago, he was a brilliant mathematician. There was a Danish astronomer named Tycho Brahe. Telescopes hadn't even been invented yet. But Brahe sat in his tower night after night after night after night. He got permission from the King of Denmark to just observe the heavenly bodies. So he took meticulous notes, and he noted that the planet Jupiter was this many degrees above the horizon and this far west of north. At what time was it? And he would carefully note the time and the position. Okay. He did that for thousands and thousands of observations and had no idea what to do with them. So near the end of his life, he hired Johannes Kepler to put together all of his observations and make sense out of them. So Kepler was a brilliant mathematician, and he didn't have calculus or anything like that. He just worked with statistical analysis, and he finally figured out, oh, okay, look at that. The orbit of Venus fits the equation of an ellipse. Okay, it's an elliptical orbit. And then he said, well, let's try the orbit of this one and that one and the other one. And he found out all the planets were ellipses, but they each had a different equation. So he put those together, and when he did, he found out the relative distances between one planet and another were described by what he called the laws of planetary motion. You know what? After 400 years, we still use Kepler's laws of planetary motion. We sent a space probe out to Pluto some years back, and using Kepler's laws of planetary motion, I think it was at least 15 or 16 years that it was in flight. And when it was getting near the end of its time in flight, we had to burn the engine for about 16 seconds. That's pretty good math. So the relative distances were originally calculated according to Kepler's laws of planetary motion. So, for instance, distance from the Earth to the Sun, we don't know what it is, but it's some amount, so we call it an astronomical unit. How about the distance from the Sun to Mars, the Sun to Venus? Well, Kepler was able to figure out the number of astronomical units to each one of the planets, but we still didn't know the absolute distance until the mid-20th century, the 1900s. Radar was invented. Radar was useful enough we could bounce it off nearby planets and determine, since it traveled at the speed of light, determine what's the absolute distance to Mars and to Venus, and that's probably about it, and certainly to the moon. We could determine the absolute distance. Now we've got a few absolute distances. We plug them back into Kepler's laws. We couldn't bounce right off Jupiter or anything like that because it's too far away. But once we determined the numbers for some of the closer objects, we plugged them into Kepler's laws to calculate distance to the Sun and to the other planets. Okay, now that we had the distances to the planets, to the Sun, and so forth, how can we tell about other stars? We now use a phenomenon called parallax, and I want you to try a little something right now. Pick something like a light that's a distance away, and hold your thumb out at arm's length in front of that light, and alternately close your right eye, left eye, right eye, left eye, right eye, and you'll see that the light seems to be jumping back and forth. Or if you focus on the light, your thumb seems to be jumping back and forth. This is a phenomenon that's called parallax. We can use it to determine distance of objects that are less than a few dozen light years away, because there's an apparent change in angle between a nearby star and the background stars, which we treat as infinitely distant. So we take a position in space, we're there, we don't have to take it. The Earth is moving around the Sun, and we see what's the angle between this star and background stars. And 6 months later, we check the same star and see what's the angle, and it should show a distance. It should show a difference, a change in angle. So the apparent change enables us to calculate the approximate distance of nearby stars, relatively nearby, maybe up to about 50 light years. But there's not enough visible change to use parallax for stars that are farther than 50 light years away. So, how do we figure these things out? Okay, there's a whole cosmic distance ladder. First, you determine the Earth's average distance from the Sun, which we've done that. And then we take a few nearby stars that are part of what's called the main sequence, and we determine their distance if they're less than about 50 light years away using parallax. And then we assume that nothing is distorting our view. We use the spectral class of the closer stars to calculate their absolute brightness. Absolute brightness, that's how bright it would be if you were at a standard distance away from that star. So we decide, okay, we're going to use this distance and determine absolute brightness. So we assume our calculations about the absolute brightness are correct, and then we apply those values to calibrate the distance of thousands of other stars on the main sequence. I'll show you something about the main sequence in a few minutes. Then we find some stars within the main sequence or that seem to be near the main sequence stars. There are stars that vary in intensity. They get brighter, dimmer, brighter, dimmer, brighter, dimmer. We call these Cepheid variable stars. So we make an assumption that the relationship between the period where they go bright, dark, bright, dark, bright, dark, we make the assumption that the relation between that period and the brightness is the same for all Cepheids throughout the universe. Is that a valid assumption? I would say no. We have no way to get out there and check it. But anyway, that's what we use. And then we use those Cepheid variable stars to determine the distance to relatively close galaxies. We look at a Cepheid variable star in a galaxy, and then we assume, another assumption, that the brightest star in each galaxy, brightest stars, have the same absolute brightness. Is there any way we could tell that? No. But we make that assumption, and we use it to calculate farther distances. And then we'll get to redshift next time. For the most distant galaxies, we use the redshift of the whole galaxy in the Hubble relation to determine the distances. So this is called the Hertzsprung-Russell diagram, after two astronomers, Hertzsprung and Russell. So there's thousands of stars on the main sequence. Here's the problem. We have to know the star's absolute magnitude to determine its distance, but we have to know its distance to determine its absolute magnitude. That is, our conclusions from the Hertzsprung-Russell diagram are based on circular reasoning, which I don't think is valid. Well, I hope I haven't gotten you too burned out on this series of the Bible and science. Next time we'll continue talking about whether there was a Big Bang, so I hope you're willing to put up with that. You may find it useful.